All right, this is the second hour of Physics 1C4, June 1st. And what we're going to do next is we're going to talk about what's called the wave equation. Let me get Discord to where I can see it. Okay, so the wave equation is something. I know some of you took Physics 1B with me. I don't remember how much we talked about this, but it was also my first time teaching it, so let's talk about the wave equation. So the wave equation is something that tells you an equation for a traveling wave, okay? So a traveling wave would be like a wave of water that's traveling along the ocean or a ripple in a pond that's traveling. And in order to describe such a wave, let's start off with the string example, because I think it's the simplest. So suppose that I have a string that is fixed at one end over here, and on the other end we have a person, and they are taking the string and they are going to oscillate it up and down like this. That is then going to produce a wave that's going to oscillate through the string that's going to do something like this. And you could say that this wave is going to have a velocity that goes this way, and it's going to have some variables associated with it. I'm going to say that this direction is the positive x direction, up and down is going to be the positive y direction, and the velocity of travel of the wave is going to be in the positive x direction, okay? So the wave is traveling along our string, and y represents the position of one piece of the string right here. So we can measure this position right here, and we would call it y, okay? And we would measure the x position relative to here. So this point right here could be like x equal to 0, for example. Maybe this point is x equal to L or something like that, right? So height of the string, x is measured in this direction, and the wave is traveling in this direction, okay? If the y-coordinate and the x-coordinate of the wave satisfies this equation, we call this the wave equation. Any wave y of x and t that satisfies this equation will be a traveling wave. So any function Oh, I forgot. How does this work? I'll just write it like this. Any function y of x and t that satisfies that equation will produce a traveling wave. So our goal today, if we can finish it today, we might have to finish it next time, will be to prove that the electric and magnetic fields satisfy this equation when you use Maxwell's equations, okay? Now, let me give you an example of a solution to this equation. Any function with the general form will satisfy this wave equation. And maybe I should write it in a slightly different way. Any function, instead of using y right here, I'll just do f. Any function of x minus vt, like this, will automatically satisfy this equation. So this equation represents the y-coordinate of a string. It is some function of x and t, and what I'm saying is as long as your function has a form that has this quantity inside of it, it will automatically satisfy it, okay? And it can be any function, okay? So examples would be this. If I have y as a function of x and t that is equal to 1 over x minus vt whole squared, then this will satisfy this wave equation. If I take a function y of x and t that's equal to something like a sine of x minus vt, this will also satisfy this wave equation, and we can prove it very easily. We'll do it really quickly here, okay? So is this one good? I don't know if this one's going to end up being too much work to do this, but you're all really good at calculus, right?
Yeah.
Maybe doing integrals is hard, but doing derivatives is always easy, right? Okay. So let's look at definitely easier, right? It's not always going to be super easy, but it's definitely easier. Let's see how easy it is in this case, okay? So here's what I want you all to do. So we're going to use this particular function. We're going to use y of x and t is equal to 1 over x minus, and I'm going to put a speed in here. We're going to pick 3, okay? X minus 3t whole squared. Okay, this is our function. And what I want to do is I want to prove that this satisfies this equation, okay? So this is what I want you all to do. According to this equation, what do we need to do? Oh, and let me just put off to the right here. In this case, v for us is going to be equal to 3 meters per second, okay? So that 3 is our velocity, right? Okay, so we need to prove that when we take the second spatial derivative, right, d2y dx2, this is going to be a partial derivative, that it's equal to the second derivative with respect to time multiplied by 1 over the velocity squared. In this case, 1 over 3 squared, which would be 9, right? So do this for me. What do you get if I take... Are you okay if I write y prime of x and t? Do you all... Okay, that's actually not the right way to do it, because these are partial derivatives. We can't do this kind of stuff. We probably could, but it would be bad form. So these are the things I want you all to do. So tell me what dy dx is, or the partial of y with respect to x is. And then use that to tell me what the second partial of y with respect to x is. And then we'll also do the same thing. We'll do del y del t, the partial of y with respect to t, and the second partial of y with respect to t. Can you all calculate what these are for me? I want everybody to do it so we can all be involved in this kind of activity. So calculate what all of these are, okay? Should I do one of them first, in case people don't know what partial derivatives are? We've actually talked about partial derivatives in this class. That doesn't mean that you know what they are, but I think a lot of people in this class either are taking 220 or you've already finished it, right?
Yeah.
I remember the last time I asked, nobody said anything, but if I'm to ask the question, hey, is there anybody here that hasn't taken this advanced math class? I don't think a lot of people are just going to raise their hand and be like, no, I haven't taken it. So I understand that there's probably some people out there that haven't taken 220. Regardless, when you take a partial derivative, all you need to know is this. If I take the partial of y with respect to x, I'm going to take the derivative of this quantity, and I'm going to treat anything that doesn't have an x in it as if it was just a constant or a number. So t, when I do this derivative, is not a variable. It's just a number. That's basically the idea. I mean, t is technically still a variable, but yeah. So can you all do this for me? Let's all do this. Let's do this in order. So we'll do this. Start with this one. Everyone work on this right here. I'll give you all a minute. Calculate what this one is, and tell me what you get. And I'll do the same thing. Okay, maybe you don't need a minute for this one. This one's pretty easy, right? Is that right? You all agree? Negative 2x minus... So I rewrote the equation like this. I think it's going to be a little easier to do that. And then we take the derivative again. So what do you get then if you do that one? Give you like 30 seconds. Who's the old dude in your picture that you linked, Cam?
Oh my god. Isn't that Lawrence?
Yeah, that's what I thought it was. That's actually him talking about this? That's pretty cool.
Oh no, it's not. Is there even like a live video of him?
Well, what is this then that you linked?
It's a whole Caltech series.
Called The Mechanical Universe? I think I've seen this, but... Oh, is it Feynman? It's gonna be Feynman, right?
Theory of relativity. As I told you then...
Yeah, this is Feynman. This is really good stuff, yeah. I've watched a lot of these videos. Richard Feynman, he's a god.
Oh my god, I binge watched these videos when I was a while ago.
Did you really?
Yeah.
He is, I know nothing about physics compared to that guy. Nothing. He is brilliant, and unlocked a lot of the secrets of our modern universe. Okay, second derivative here. We just take -3, we bring it down in front, so -3 times -2 is +6, and that's equal, then we multiply that by x minus 3t, and we just subtract 1 from the power. Okay, does everyone agree with that? Okay, let's do these two then. Also, I'll just let you do both of these, and then we'll just do them together. So take a minute and calculate the partial with respect to t, and then second partial. Okay, so hopefully that was enough time. First derivative here is what? We bring the -2 down in front. And then reduce the power by 1. What else do I have to do?
The derivative
Multiply by
of the
-3.
inside.
And multiply by -3, because the chain rule, we have to also multiply by the derivative of the inside. So then we do -3 multiplied by this, so we're going to get +6. Do it again. -3 times 6 would be -18 times x minus 3t to the -4. But again, we need to multiply by -3, so -3 times 18, I don't know what that is, 54 maybe?
Yeah.
Now, did I mess up my minus signs? I didn't, because it's still going to be, yeah. Okay, so we get a positive answer, which is good, because I don't see any negative signs up here. So we get 54. Okay, so is this actually going to work out? I don't know. Guess we'll see. So what we had to prove was that our function, x minus 3t to the -2, satisfied the wave equation, right? And that meant that I needed to show that this quantity was equal to this quantity divided by v squared. Well, they definitely have the same functional form, so that's good, right? And what would 1 over v squared be? Well, v in this case was 3, right? I'm not using units here, so I apologize for that, but something tells me you all don't mind. 1 over 3 squared times this, which is 54, times x minus 3t to the -4. And that's going to give us 54 over 9, which is 6, right? So it's proved then, right? This is equal to this. And now, if you want to, you could do this for a sine wave if you want to. Or you could just pick any function you want to. It doesn't matter what the function is. It does not matter. As long as the function has this general form, it has some x minus vt raised to a power, or the function x minus vt itself, right? E to the x minus vt, e to the ix minus vt. It doesn't matter. You pick any function you want. Any function. It will automatically satisfy this equation. So that's nice. We have a whole class of functions that will satisfy it, right? There's no single solution. There are an infinite number of solutions, basically, right? To this. And that means there's all kinds of different waves that you can have. And we call this the wave equation because this produces a traveling wave. So that's a mathematical explanation using calculus and modern kind of like algebra, right, to describe it. But I think it's helpful to look at what this looks like, to see how could this actually be a wave, right? How is this a wave, right? You look at this and you think, how is that a wave? When I think of waves, what do you think of? When you think of waves in mathematics, what do you think of?
Like
Y
Sine.
equations.
What do you think of, John? What'd you say?
The Y equations, I said.
The Y equations, okay. And what else? What else do you guys think of when you think of waves in math?
Wait, what are the Y equations?
I think he meant something like this.
Yeah.
I think of like sine, cosine.
You think of sine and cosine. Do other people think of that too? When you think about mathematics, you think about when you learned about waves in mathematics, you probably first learned about sines and cosines, right? And then you talked about how the frequencies could change and how the periods could change and the amplitudes, all these different things. But when you think of waves, you think of sines and cosines. At least that's what I think of. Because, I mean, yeah, it's a wave, right? So here's what we're going to do. You can do this on Desmos if you want. I haven't used it very much, so I'm not super familiar with it. But what I'm going to do is we're going to plot our function. So our function was x minus 3t to the negative 2, right? So we're going to plot x minus 3t to the negative 2. Do that just in case. And we'll plot it from whatever. We'll let it figure out the range. Okay. Now, if I just put this in here, there's going to be a problem. We're just going to do it, and I'll show you what happens. These things, they don't like multivariable functions. Okay. So it's going to produce a plot where x is going to be one axis and t is going to be one axis and the function is going to be the other axis. And you get a three-dimensional plot. This isn't really what we want. Okay. What we want is we want to look at the wave as it moves through time. Okay. So what we're going to do is we're going to place the t here with 3 different values. Okay. We're going to plot at t equal to 0. And then we're going to plot the same function at t equal to 1 second. Because we don't see time all at once, right? We see time in intervals. 0 seconds, 1 second, 2 seconds, 3 seconds, right? Things happen over time, right? We don't see time all at once. Maybe some distant civilization or some future advanced civilization will be able to do it, but we can't do it. So this is going to plot x at t equal to 0, t equal to 1, t equal to 2, and it should give me 3 different graphs, basically, right? If I did it right, I might have messed up the syntax. I don't know. Generally, Wolfram Alpha is pretty forgiving with syntax. And there we go. There's your traveling wave. So this is the wave at t equal to 0 seconds. After 1 second, it has moved right here. And there's your wave pulse at t equal to 1 second. And then there's the wave pulse at t equal to 3 seconds. It's moving. Can you see that it's moving? From the blue to the purple to the yellow?
Mm-hmm.
So that's a traveling wave. That's what a traveling wave is. And the waveform, right? The waveform is this. It's the function 1 over x squared, which is basically just it has a pole at x equal to 0, right? So these are asymptotes, but it's still like a little pulse that travels along to the right. Does that make sense, what a traveling wave is?
Mm-hmm.
Yeah.
All you need is just a function that looks like this, because this function, you can prove that any function you choose, you will automatically satisfy this equation. I think you can prove it in general pretty easily, actually. Maybe I'm wrong, but... Okay. I mean, it's pretty... Do we want to talk about it for a second? Maybe is it obvious to you all why this type of function satisfies this? Look at what we're doing. You're taking the derivative twice with respect to time, right? If I take a function that looks like this, and I take the derivative twice with respect to time, no matter what the function is, I'm going to use the chain rule, and I'm going to multiply by negative v twice, right?
True.
We did it here when we multiplied by the negative 3, and we did it again on this one when we multiplied by the negative 3. So you're automatically going to get a positive v squared that's going to show up right here after you do the integral. The derivative. After you do the derivative, you're going to get a positive v squared. That's going to cancel out with this v squared, right? And then because the x doesn't have a coefficient on it, then you're not going to get anything over here. And x and t both show up as the first power, right? It's t to the x to the 1 and t to the 1. So there's no other things that can show up in this equation, right? Once you take the derivative with respect to x, you're going to maintain the function. Our function was x minus 3t, right? You're going to maintain the function because, like, there's no x. If it was x squared, we'd also have to multiply by 2x on the outside, right? And that might be kind of hard to get an x over here when you're taking time derivatives. Okay. But do you all see it, why it works?
Yeah.
Okay. So it's actually pretty obvious when you just kind of inspect the way that the wave equation works. That being said, I'm sure when you all look at this equation, it's not immediately obvious to you that this will be the general form. And when you look at equations like this, it probably makes your brain kind of glaze over a little bit because you're just like, man, what is going on? There's so many things here, right?
Looks amazing.
But that's okay. And for people like Cam, maybe it looks amazing. It is a very impressive idea that any traveling wave can be described by one equation. That's pretty amazing. Now, this only works for... I think I left out one detail here. I believe this only works for transverse waves. But it turns out that's not entirely true. Because I'm pretty sure if you replace the y here with pressure, it also works for sound waves. So I think it works for any wave, actually. But what the y is might change, okay? I used the example of a string where the y-coordinate was the height of the string, and it basically represented a pulse that traveled, right? All right, I need to move right along. So the next topic, before we move along, any final questions about the wave equation in general? Do you all agree that if I can prove that the electric field also satisfies this same equation, and the magnetic field separately satisfies this same equation, that if we can prove that, it'll prove that there is such a thing as an electric or a magnetic wave, right? That's our goal. Does that make sense?
Yeah.
As long as I can write down an equation like this that comes from all the stuff we've learned this semester, i.e. Maxwell's equations, and at the end, I get an E here, and I get an E here for the electric field, we will have proved that the electromagnetic wave is a real thing. So, let us try to do that. Now, before we get into the math of how we're going to do that, we need to define what kind of waves we're going to be talking about here, okay? So we're going to be talking about what are called plane electromagnetic, so I'm using the word EM, electromagnetic waves. We're going to be talking about plane electromagnetic waves. Now, what are these? Suppose that you have a star, okay? And it's emanating light waves, okay? The way that it's going to emanate those light waves is going to be somewhat similar to the way that waves ripple out in a pond. You're going to get ripples that kind of go like this. And what you're going to find is the farther away that you get from the source, the curvature of the wavefront, okay, so these are going to represent wave fronts. The curvature of the wavefront is going to get smaller and smaller over time until, when you get far enough away, these wavefronts are going to start to appear as just straight lines because the curvature is going to be so incredibly intense. Or sorry, the curvature is going to be so incredibly large. And this is what we're going to represent as plane waves. The idea of waves that are traveling in this direction, so this is the direction of travel, the velocity of the wave is this way, and this is a plane wavefront. Okay? It's literally like a big plane, so, use this, I guess. The wavefront is like a plane, like a piece of paper, right? And it is traveling through space in this direction. So we can represent it by using like a rectangle, basically. More like, I can't use a rectangle, I'll have to use something else. So our wavefront is going to have a form. It's going to look something like this. So there's a plane, just what you think of as a plane, right? And within our plane, we are going to have electric and magnetic fields, okay? So what they're going to look like is, let's use green for electric fields. Something like this. You're going to have an electric field like this, and you're going to have a magnetic field perpendicular to it. So at right angles to one another, we're going to have, so this is a right angle right here. The green represents an electric field vector. The blue represents a magnetic field vector. And all across the plane, these are going to be, I don't know if this is going to let me copy paste this, did it? Yeah, okay. All across the same plane, here, let me get rid of the pieces that I copied that I didn't want. So all across the entire plane, these values are going to be the same, okay? All across one plane, which is going to be a very large plane, our electric and magnetic fields are going to kind of be like in phase with each other, meaning they're all going to have the same magnitude at this point, okay? All along the plane, the values are the same, but when we come to a plane that's right next to this one, so consider plane 1 and plane 2, like this here, that's where they are going to get different, okay? So this is going to be successive wavefronts, right? So if this is a wavefront, and this is wavefront 1, and this is wavefront 2, when we expand them out, they're going to look like this, and they're going to look like this. So these are successive wavefronts. Maybe they represent the peaks or something like that. And when we get to the second wavefront now, what's going to happen is that maybe our electric field's a little shorter here. It could be a little longer. Maybe the magnetic field is now also a little bit shorter, a little longer. We're going to find that there is a fixed ratio between these two, which is related to the speed of light. Maybe the magnetic field gets a little bit smaller. And then, same thing down here. Same thing down here. So imagine a plane, and on that plane you just have a bunch of field vectors, okay? And on a given plane, all the E fields are the same. Do I need to write that down? I don't know. I probably should, because it's kind of... So on a given plane, or a given wavefront, all E and B values are the same. But they change from wavefront to wavefront, okay? I'll just stop right there because I know this is really complicated. Does this make sense?
Yeah, yes.
Does anyone have any questions?
Well, what's causing like the magnitudes to change?
This. Charged particles that are oscillating. That. Is that a good enough answer?
I was just asking, like, as you go from wavefront 1 to wavefront 2, like, it's because it's farther away from the source that the magnitude's like getting smaller?
Okay, let me draw another picture. Will this thing let me get like a sine wave? It probably won't. All right, let me do it like this. So here's our source right here in the middle. All right, no. Let's say the source is way over here somewhere, okay? And we're looking at a bunch of successive wavefronts, okay? Like one right here. And then one next to it. So each of these, this is gonna be like a side section of... What's going on? Why won't it let me move this? Oh no. Oh no, what just happened? I'm really weird. I think I just selected the whole document and I just moved everything over a little bit. Okay, well that's not good. Doesn't really matter. We can just zip this way a little bit. Okay, all I want to do is click this. There we go. And then move it up here. Okay, that wasn't so hard. All right, so you were asking what causes it to change from wavefront to wavefront. Okay, here's the idea. Suppose that I draw on this picture right here a wave, like a sine wave, and we'll make it go like this. It's going to peak right here, and then it's going to go down like this. Okay? and then it'll continue, you know, down this way and back up to here. Okay. So this is going to represent from plane to plane. So maybe this is plane 1 and maybe this is plane 2 right here. Okay. What the values of the electric field are going to be. Okay. So here there's going to be an electric field vector. We can draw it in at this location on this plane. Oops, that's not the way I meant to draw that. That's going to look like this. There's going to be an electric field vector that comes up like this on that plane, and then there's going to be an electric field vector that comes up like this on this plane. So the values will be slightly different. Actually, I shifted that just a little bit so it's like a pixel off. So this is like the electric field at this location. Maybe we call it E1. And this is like the electric field at this location. Maybe we call it E2. And then perpendicular to this, there's also magnetic fields, okay? But yeah, like all along this, the value of the electric field at different locations is going to be changing, okay? But what I'm saying is if I come to another point, like right here, on my plane 1, that the size of the electric field at this location is going to be the same as the size of the electric field at this location, okay? And why would that be the case? Well, it would be the case if the source that this light was coming from was all kind of synchronized, basically. Like a bunch of particles all moving in unison that are producing these waves. So that's what I mean when I say that the electric field is changing from this position over to this position here. Okay? Does that make sense?
Yeah.
Okay. Let me show you another picture. I can't possibly draw this. I think there's going to be one on the Wikipedia article that's going to look like what we want. This picture right here. This is what's going on. It's going to take me forever to draw something like this. So you have a wave. It's propagating in this direction right here to the right. And the electric fields are represented by this blue color. And the magnetic fields are represented by this red color. And a wave front would be like a cross section right here. Does that make sense? So as I move from one wavefront here to a second wavefront right here, the size of the electric field is changing, but it's kind of following like a wave like this. Does that help?
Yeah, it's more due to like the oscillation of the charged particle, right?
That's where it's coming from. 100%. That's exactly where it's coming from, right? That's exactly where it's coming from. And then we expand it and say, okay, now it's not just one wave, right? That would be silly. How could a distant star have just one wave coming out of it? That's silly. The star is made of gazillions of particles that are all charged and they're all oscillating. So you're going to get a whole bunch of stuff happening. But what we're looking at are waves that act in such a way that they make our lives simple for doing the calculation. And that's by saying this, that on a given wavefront, all the electric and magnetic fields will be the same, but they're going to change as you move from wavefront 1 to wavefront 2 to wavefront 3, etc. They're oscillating just like this down here. All right. That is a plane wave. Anyone have any questions about plane waves? No? So, here's what we're going to do. We are going to... Can I get an XYZ axis out of this? I can, right? We'll do it like that. Alright, so here's how we're going to name our axes. This is going to be X. This is going to be Z. And this is going to be Y. Okay? And on our three-dimensional coordinate system here, I'm now going to drop in our plane waves. Maybe I can just copy this. Maybe I can just copy these. Should work. They should fit on my picture here, and then I can just manipulate it until the... Oh, look at that. They actually look like they line up pretty well with the direction of my z-axis here. All I would need to do is just... what I want is that z-axis to basically be parallel to these lines here. So I'm just going to do something like that. Does that help? That's helping, right? Yeah, so that's not good. This gets better, 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 better. Something like that, right? And maybe even I could just line it up. This is the easiest thing to do. What am I doing? Being stupid. You can just straight line this up here until it eventually is parallel. Close. There we go. That's pretty parallel, right? It's not good enough.
It looks good.
That's fine. It's good.
I'm very like OCD with stuff like this.
Particular.
There we go. That looks good. You can't even see the lines anymore. Okay. So this is our picture. Okay, right? We got the z-axis coming out this way. So z, it's kind of moved over a little bit. We got the x-axis going to the right. Okay. And the wave is propagating in the positive x direction. Okay. So this is the velocity of the wave. Propagating in the positive x direction. And what we're going to do is we're going to say that the distance between these two wavefronts, we're going to call that delta x. Okay. And now what we're going to do is we are going to use Maxwell's equations. Okay. So the first one that we're going to use is Faraday's law. We're going to calculate what is the integral of E dot dl in this situation. Now, in order to do that, we are going to need a path around which we can take this integral. Okay? So, what's a color that's going to stand out on this? Probably purple will work. This is the path that we are going to take. We're going to do a path that's actually going to be a box, isn't it? It's actually going to be a straight up box with the way that I drew this. So this is going to be our path. And I'm going to try a different color and see if it stands out better. That's not good. Yellow is kind of... It's okay. I mean, you can see it pretty well. You can see it. So this is our path, and yeah, this is our path. And why do we need a path? Well, because we want to calculate an integral like this. Okay. So next what we'll do is we are going to talk about what the values of the electric field are along this region here. Okay. So delta x, this is our path, and we want to travel in a clockwise direction around this. I think the path that we're going to go around is this way. That's what I think. That's the right way to do it. Okay. Now, along our path, we're going to have a situation that is going to look something like this. We're going to come up with a simplified version of this. So let's take just a normal xy coordinate system. In fact, all we're going to need is just this, actually. Take a normal xy coordinate system. Okay. Let's make our coordinates the same color as they were before they were green. So this is my x direction. This is my y direction. And this is my path. Okay. Now, on my path, remember that I said that along a given wavefront, the value of the electric fields are going to be the same everywhere. So, on the left edge of my path over here then, I'm going to have an electric field vector that's going to point straight up like this. Surprised that it didn't make that green. I thought I made it green. So on the left edge of my path, I'm going to have an electric field vector, and it's going to point like this. And that's what we're calling E1. On the right edge of my path, then, I'm going to have an electric field vector that we're going to call E2. Because that's what the electric field is at that location. It's a little bit different. So we call it E2, make it a little bit different size. We already said that the size of our path was delta x in this direction. The other piece of information we're going to need to know is the height of our path. So we're going to call that A. And I think we have everything that we need then. So what I would say is that when we are doing this path, when we travel along the bottom right here, we're going to be doing E dot dl, right? So I guess actually on my picture, I'm going to want to draw dl. So this is what dl is going to look like, right? It's going to be a line element of my path. So going along our thing right here, what we're going to get is, along the bottom, E dot dl is going to be 0, okay? along the right side as I travel along here, what we're going to get, I think there's enough room to start this up here. When we do E dot dl, we're going to get, along the bottom side, we're going to get 0. Because the electric field is only oscillating up and down, which means it can only point up and it can only point down. It cannot point left and it cannot point right, which means the angle between the electric field and dl along the bottom here is equal to what?
This is 0.
0, right? Yeah. So we get 0 along the bottom plus. Along the right-hand side over here, remember that we said that the electric field is changing from front to front, so the electric field here is E1 and the electric field here is E2. But along a given front, we know that the electric field is basically, along this side, is just E2. So when I do E dot dl, if the E is constant, I can basically pull it out, and I'm doing E times the length. So we're going to get something like E2 multiplied by A. Does that make sense?
Yeah.
All right. And then as we keep going around here, when we go along the top, we're also going to get 0. And then we go along the left-hand side over here. Now our dl vector is going down. Here, the dl vector is going to go this way. So now E is up and dl is down. So what should I write down for E dot dl on the left side?
Minus E1A.
Okay, so minus E1 times A. All right? Now, ultimately what we're going to be looking for here is what the electric field itself is, which means that we're looking for not just the value of the electric field E1 and the value of the electric field E2, but in general how the electric field varies through space. So in order to do that, we need to know what E is and how it changes from point to point. So what I would say then is that when we look at our picture right here, if there is in general some electric field E, then E1 is basically equal to the electric field at some point x. And it's important to understand that this electric field is also going to have a time component because it's moving through space. And I'm just going to say that the value of the electric field here at the point that we're going to call x, so x is just the location of the left side of my box right here, we're calling E1 E of x and t, and then I'll call E2 to be equal to, sorry, it doesn't really look like a 2, E2 to be equal to E of x plus delta x, comma t. Does that seem reasonable to you all? Because
Yeah.
the coordinate of this point right here is x plus delta x, right? So then the value of E2 is going to be the electric field, the function, evaluated at the point x plus delta x. And our goal here really is, what is this function going to be? We don't know what it is. So if we put these ideas into that equation, what we end up getting is now, kind of running a little low on space here, I need to be kind of careful. When we do E dot dl, we're going to get E2 times A, which is this,
Oh, kind of looks like the beginning of a derivative.
yeah, you realize that faster than most people do. Here we go. Does that make sense? All right. So we found that that's the value for E dot dl. Okay? That is the value for E dot dl. Now, the next thing that we're going to do is we need to compare this to the other piece of Faraday's law, which is the time derivative of the flux. Right? Because Faraday's law basically relates these two quantities right here, right? So let's do that. Let's figure out what the size of the flux is through the rectangle, okay? We'll put that over here. Maybe use a different color. What is the magnetic flux through our path? Well, when we look at our path right here, we can see the area. What's the area contained by this path?
A delta x.
A times delta x. Okay, so first of all, we know that the area of our path is equal to A times delta x. Okay. Now, in order to figure out the magnetic flux, all we need to know is what the value of the magnetic field is. Now, we're going to kind of do a little bit of I don't know if it's a cheat, but it is what it is. It's just something. I'm going to say that my area vector is going to be pointing out because the path is going around in a circle like this, and if you wrap your fingers in that direction, your thumb points out of the page. And what direction is the magnetic field? Well, the magnetic field appears to also be pointing out, right? So let's just say that the size of my box, delta x, let's assume that it's kind of small, and that we can basically say that over the path that we're taking, if the delta x is small enough, let's say that we just take the average value of B, okay? We just average the value for the magnetic field in this location, and we just call that B, basically, okay? So we're going to use just B to represent kind of like the average value over the path. And this is largely just to prevent us from having to do any kind of complicated integrals here or anything like that. So we're going to say B represents the average value of the path. Well, if that's the case, then the magnetic flux through our path should just be equal to the size of the magnetic field multiplied by the area, right? Does that make sense?
Yes, yes.
Okay. Now I meant to add some other complications into this to be really clear about what's going on here. Okay, so I have to kind of go back through both of the things we just did, and we're going to have to add some subscripts. What direction does the magnetic field point in?
In the positive z.
Positive z. And in principle, remember, going back to our picture right here, it's eventually going to point in the negative z direction too, right?
Mm-hmm.
Okay, different axes here, but you get the idea. Okay, so really, when we talk about B, we mean the z component of the magnetic field here, right? This is just the z component, because it only points in the z direction, right? In principle, we could have a more complicated wave that has components that point in all of the directions, but this is just the z component, basically. And what about the electric field? What component of the electric field are we talking about right here? What direction does the electric field point? Does it point in the x, y, or z direction? Y direction, right? So let's just say that E1 now, we're going to call it EY of x and t. We call this EY of x and t, and we call this EY at x plus delta x and EY at x and t. I feel like this is really complicated if we do it at first, but if you just put them in later, it's okay, right? So it's the z component of the magnetic field we're talking about. It's the y component of the electric field that we're talking about, right? Okay. So now we want to put these together, right? We've got our flux. We've got this. But we can't combine them together unless we use Faraday's law, right? So Faraday's law tells us that the integral of E dot dl should be equal to the negative of the time derivative of the magnetic flux. So let's put these together. What we have on the left-hand side is what we wrote right here. To save time, we'll just copy-paste it. So that's the left-hand side of my equation. Let's just move down just a little bit so we don't have to worry about these axes. The right-hand side of my equation is going to come from the flux. So my flux is bz a delta x. Move this down just a little bit. So that's the flux up there, bz times a delta x. So this is going to be equal to negative ddt of bz a delta x. Notice something cancels, right? What's going to cancel out?
All the A's?
Yep.
The A.
All the A's go away. That's nice. Delta x was just the distance between these 2 points, so it's not going to vary with respect to time. So we're going to pull delta x out of here. It's a variable that represents how big do we make our path, right? So I'm going to divide delta x to the left-hand side over here. So what we're going to get is ey. Oops, sorry. Let's keep the color the same. We're going to get ey of x plus delta x comma t minus ey of x and t. So this is the electric field. They're both evaluated at the same time t, but this is the electric field at x plus delta x, and this is the electric field at point x. We divide all of this by delta x. The right-hand side of the equation is very simple now. It just says negative del bz del t. Actually, it's not. Okay. You all hate me if I do this. B is a function of x and t, so this should really be a partial derivative now. Okay. So this is the expression that we get. Now, the last thing that we're going to do, and I think Cam hinted at this earlier, maybe you can tell me, what am I going to do for this next step here? What's going on with the left-hand side of that equation?
We're going to let delta x go to 0.
Yep, we're going to take the limit as delta x goes to 0. Because this thing on the left-hand side, as you hinted at before, you noticed when we got to this line right here, you notice that we're doing something that looks an awful lot like the definition of the derivative that you probably learned either in your pre-calculus class or in your calculus class. This is the definition of what a derivative is. A function evaluated at some point x plus delta x, and a function evaluated at a point x. You take the difference of those, you divide by delta x, and then you take the limit as delta x approaches 0. All of this thing on the left-hand side is also known as the partial derivative of EY with respect to x. And this is equal to the negative of del BZ del T. That's the first half of our derivation. And remember, this basically is, this came from, directly from, applying Faraday's law. So all we've done is we've applied Faraday's law to our fields. That's all that we've done, right? And it gave us this relationship right here. Now, is this a wave equation? What do you all think? Is it?
There's no second partial derivative.
That's right. Remember, our goal, right, is to get to here. And we're not there yet, okay? So, we got to do one more thing. And the next thing we're going to do is we're going to use Ampere's law, okay? And we're going to do another loop. But this time, we're going to do a loop integral for the magnetic field. It's 4:40 p.m. We've been going for almost an hour now. So I think that's where we'll start next time. We're going to start from this picture, and we're going to do the exact same thing, but we're going to use Ampere's law, right? So Ampere's law was, where is it? This one here. But one thing that we're going to have to do to make this work is we're going to need to get rid of this term right here, because there's not going to be any electric currents in what we're describing. So we're going to go ahead and set the current equal to 0, and then we're going to do the exact same thing we just did. We'll start class with that next time, and then what we'll do is we'll get similar results. I'm pretty sure the result is exactly the same. I think the x's and t's are swapped. And then I don't think there's a negative sign, because there's no negative sign on Ampere's law. And then we'll combine those together. We'll prove that the electric field and magnetic field satisfy the wave equation, and then we'll look at the effects of that. The what's called the Poynting vector. We'll look at radiation pressure, the fact that light itself can exert pressure and momentum, and then we'll talk about solar sailing, and that'll be the last class before the final. We will also, next time, I'll do a general summary of like Physics 1C, so I can hopefully help to just give you a kind of summary of like what kind of things you need to know for the final, basically. That's a bad way of putting it. I'm just going to summarize all of Physics 1C in kind of a short amount of time, like in about a 5-minute explanation of what we've learned this semester, and kind of just the big picture to tie everything together. Okay, so that's what we'll do next time. Before we go though, does anyone have any questions about all of this?
We took the limit as delta x went to 0 of the thing on the left side. How'd that become the partial derivative?
Sure. Okay. So I'm just going to refer you to your calculus textbook, or
It's a definition of the partial derivative.
that's basically how they're defined. Okay. So first of all, the definition of the derivative, how well is this described right here? Is this? That's almost exactly what you learn in your you might not remember this, because I know that like from year to year, like you don't retain every bit of information that you learn, right? But at some point when you were first learning calculus, they put this formula on the board in some form, okay, f of x plus h minus f of x divided by h, limit as h goes to 0, and they said this is the definition of what a derivative is. And you can prove it for yourself really simply. If you put f of x plus h into a function like this, so I put x plus h squared and x plus h here, you can prove that you'll get 4x minus 16 from this formula. Very easy. Super simple. You can try it yourself in case you don't remember it. Does that sound familiar to everybody?
Yeah.
Yeah, I remember doing that.
Yeah.
You guys all remember doing this. It's like super early on, and then you learn it, and then after you learn it, you start to learn the derivative rules, right? Like the power rule and the rules for sines and cosines, and then you forget it because you don't need this, right? So how is a partial derivative defined, and how is it different? Well, what do you notice that's different about this expression compared to what we had? What's the one difference?
We have an extra like t in there.
There's a t. And this is the key thing. This one doesn't say t plus delta t. It just says t, right? And this one says t. So that means that it's the same time. That means that time is constant, which is the definition of what a partial derivative is, right? When you take a partial derivative, you hold one variable constant, and then you take the derivative with respect to the other variable. So yeah, this is in Calc 220. This is how you would have defined, I would guess, the partial derivative. Now I don't know. I didn't take 220, but is that right? Is that how you guys define it? Yeah.
Mm-hmm.
Yeah, that makes sense.
Okay, good, great. All right, well, any other questions? That was a very good question. I'm glad you asked that, because I'm sure other people had the same question. I'll put up something for you, Henry. But absolutely, like basically, if your exam time last time was 2:45, you'll probably be exactly the same time. But I'll put up a. It's pretty much going to be the same. I believe there's. I can't remember if anybody dropped this class or not. I just don't remember. Certainly, probably somebody dropped this class. There were some people that never showed up and never turned in any homework that contacted me and told me that they were going to have to drop the class, I think. But maybe I'm thinking of 1A. Regardless, should be the same times. So if the time for you was bad last time, just let me know and we can work with that. I know next week is going to be probably really hectic for all of you because there's going to be a lot of finals going on, and your finals might start to conflict with both the time that we have for the exam, and they might also conflict with the time that I submit the problem to you, right? So if you're in the unfortunate situation that you have like a final exam that goes from, let's say, 11 a.m. to 2 p.m. on Tuesday, and you're scheduled to present your problem at 2 p.m. on Tuesday, and I mail you the problem at 11 a.m., you're really not going to have any time to do that, right? If you're doing an exam from 11 to 2. So if anybody's in that boat, please let me know, and we can move the times around. Can move you later in the day. Can move you way later in the day if needed. Like we can go after 6 p.m. if needed or something. So just, does that all make sense to everyone? I know your lives are going to be chaotic next week. I don't want taking this exam to be more difficult for you than it needs to be. So just understand that I will be flexible with you and fair, and I'll try to be nice about it too. Even though sometimes I get kind of cranky when people ask me to change things. It doesn't mean that I don't want to help you. I do want to help you. I absolutely do. Okay. I extended your homework assignment by 1 day too, by the way, because someone last night pointed out on Discord that there was this kind of weird having it due on a holiday. And so I went ahead. You have another night to do the AC circuit. Is it AC circuits? Is that the one that's due this week?
Yeah.
Yeah. So you got another night to do that. So that homework's really short too, anyway, right? Isn't it only like 6 problems?
6 problems.
Yeah. So I don't even know if you needed an extra day, but you got it. So
That's a problem.
But they have many parts, though. Yeah.
They have a lot of parts, exactly. That's why I didn't want to give you like 12 problems, because also they're kind of repetitive, right? They're not the most like interesting. I don't know.
Mm-hmm. Don't forget that capacitors in series lessens the capacitance.
Yeah.
That's right. That's
People
exactly
do
right.
not.
That's how it works. That's right.
Professor,
What's up?
I had a question about the double slit experiment.
Okay.
I've seen this documentary. They also use it for subatomic particles.
Yeah, that's right. So the effect. So this goes directly back. This is a great question. This goes directly back into what we were talking about at the beginning of class when we were talking about the double slit experiment. So, in the 20s, I don't know, about 100 years later, actually, I think it was like 1825 or 1830, about 100 years after Young and Fresnel, this idea was kind of growing within physics that the concept of a particle and a wave was starting to become blurry. And there was a guy named De Broglie, who was a graduate student in France, I believe. His name looks like De Broglie, but I believe it's pronounced De Broglie. And he, I think it was in his thesis or his dissertation or something like that, he proposed the idea that you could come up with a wavelength for a particle by taking what's known as Planck's constant and dividing by the momentum of the particle. And it's interesting because it's something that's like, well, anyway. So he proposed the idea of wave-particle duality. He said that it's conceivable that this idea of the wave and the particle is not something that's so concrete like we thought it was, and because light waves sometimes act like particles in, for example, the photoelectric effect, the Compton effects, and some other things you'll learn about when you study the history of quantum mechanics. Because light sometimes acts like a particle, and we knew that light was a wave, remember? It was a wave, we proved it. Light has to be waves in 1820, Young and Fresnel, that's the whole thing. But then Einstein showed that light has to be a particle with the photoelectric effect. So you have two different experiments that can't be reconciled with each other. And so De Broglie says, well, what if they can be waves sometimes and they can be particles sometimes? What if our understanding of what they are is not complete and they're both waves and they're particles? And sometimes in some experiments we measure them to be waves and sometimes we measure them to be particles. And so he extended that. He said, well, what if we could say the same thing about electrons? Electrons we think are hard particles, but maybe they're also waves. Let's reverse it, right? If light can be a particle and a wave, maybe an electron can be a particle and a wave. And so to get back to your question, John, subatomic particles, the double slit experiment, eventually someone got a sophisticated setup and they were able to take a beam of electrons and pass them through a crystal. This was what's called the Davison-Grommer experiment, I believe is the first time that it was done. I could be wrong. The first result. And they showed that a beam of electrons being passed through a crystal, where the crystal acts as your slit. And why a crystal? A crystal because the separations between the crystals can be like angstroms, like nanometers, really tiny separations. So you get a natural slit that we probably couldn't construct ourselves. The light experiments, you could actually see the size of the slits, even though they were like micrometers in terms of size. You can see it. So you pass electrons through a crystal, and lo and behold, you get an interference pattern. So it turns out that even electrons, which we think were hard particles, could also exhibit this phenomenon called interference. And then, in case you thought for some reason, oh well, maybe electrons are actually just waves. Then maybe we were just wrong this whole time. Electrons aren't particles. Maybe they're just waves. Well, they did the same experiment way later on with what are called buckyballs. Something I was talking about with the physics club this week. They were sharing with me that they had learned from their 1D class that they did the same thing with really big pieces of matter. Buckyballs is like carbon-60, I think is what it's called. Basically 60 carbon atoms in the form of a soccer ball. So imagine sending soccer balls through a double slit and still seeing an interference pattern. So yeah. Does that answer your question? Is that what you're talking about?
Yeah. I'm sorry, they got the same result with the big objects?
Yeah, not like baseballs, okay? But
Okay.
still like atoms. I mean, not really atoms. It's a compound. What do you call it? What do you call the different variations of carbon? What are those called?
Isotope?
Isotopes, yeah.
Oh wait, no.
No, it's not. Isotope is a different number of
Isotope.
neutrons. So like carbon 12, carbon 14, those are isotopes. What is it called when you have like graphite, charcoal, diamonds?
Like anode. So
Are they called like
something-
isomorphs or something?
Isomers?
Is it
No.
isomer?
That's for molecules. Yeah.
Okay, I suck at chemistry. So like I never took a chemistry class like the kind of chemistry classes you all take. I mean, I took AP Chem, but then My chem class in college was more about like reading Lavoisier and reading about phlogiston and all this weird stuff, but I don't know what it's called. Anyway, it doesn't matter.
Yeah.
But carbon-60, or buckyballs, I'll show you a picture of it. Buckminster Fullerene is the name of it. This is a picture of it right here. It is, so see, it's like these, aren't these called benzene structures? Something like that?
Yep.
Yeah.
So it's like you take a benzene structure and you organize it like a soccer ball. I don't know the way to say it. It's like a soccer ball. Yeah. Yep. So, anyway, even these, which are huge. What's the molar mass? 720. That's bigger than anything on the periodic table by a long shot, right?
Yes.
Yeah. So, these things are massive. Their density is 1.65 grams per centimeter cubed. I think this is actually denser than air, right? A little bit denser than air. Because I think air is about 1 gram per centimeter cubed, probably. Anyway, even these things, which are huge, they were also able to interfere with each other. And man, that sure looks like a particle, right? I mean, it sure looks like a hard object, you know? So what on earth is interfering? You know, what is it that's interfering? And, well, you'll probably learn about it in Physics 1D. Like, where's the interference happening? So, maybe Dehao Lin knows. What is it that's actually interfering in the case of these particles, Dehao? Do you know? I don't know if he's still here. He is still here.
Good here.
Do you remember, or did you guys talk about what is the thing that's actually doing the interference then? I mean, in the case of waves, it's like you got a maximum and you've got a minimum and they're canceling out, or you have a maximum and maximum and they're adding up. That's what interference is basically, right? But what is the particle interacting with? What's happening?
I don't think we talked about that, but like we just talked about like the wave interfering and like some part adding up to create a lighter slits, and then
Yeah.
the other like they diminished in between.
Did you guys talk about the wave function?
Yeah.
That's what
Really recently.
that's what the interference is. It's the interference of the wave function. The probability wave, right?
Yeah, the probability. But I think we'll learn something about the infinite squared well.
Mm-hmm. No, there's another piece about this that's really crazy. Someone actually posted a meme about this. In I think it was in the they probably posted it in the memes channel, right? Here it is. I'll link it to you. So the crazy part is that it turns out that the interference phenomenon, the interference effect, it actually goes away when you look at it, which is just crazy. So this is
a good one.
This is the meme. The idea is that so he's looking away, and then here's this double slit. You get the interference pattern, and he looks at it, and then you get this. And the idea is that what happened is that they did this experiment where, you know, basically what it says, the idea of the double slit experiment, what people always say is that if you have an electron and it's passing in this direction and it comes to the slit, there's some probability that the electron basically passes through one slit. There's a probability that the electron passes through the other slit. There's a probability the electron doesn't pass through either slit. But then there's also a probability that you can calculate that the electron passes through both slits. And the interference of all these possibilities is what produced the interference effect. Okay? So the crazy part is be like, well, that's silly. Certainly the electron had to pass through either the bottom or the top, right? And so someone got the smart idea to be like, hey, what if we actually watch and look at what happens to the electrons as they pass through here? And what happened was that when they look at them and they observed the electron, you no longer get an interference effect. So it's almost like nature has these interference phenomenon, but if you look too closely, they disappear. And the reason for that is that when you look at them, when you measure them, you remove the wave property. You do what's called collapsing the wave function. And now we're getting well beyond the scope of this course and saying things that I haven't even described to you what they mean, so I don't want to say more, but anyway, this is a pretty good meme to kind of state that idea. Anyway, any other questions? I think it's definitely a good place to stop. We're 4:57, it's a very long video.